we've allotted an hour and a half. We don't need to take all of that if we don't need it, but we may need it because we have a lot of smart people in here that will have a lot of questions and comments. So just know that our presentations will probably take up the first hour of that, and then there'll be more time for questions. So welcome everyone today to our Big Coat Climate Action Meeting, and thank you all for joining us. Our session today is focused on decarbonizing existing commercial buildings. As most of you know, over 50 cities in California have now passed electrification ordinances, and California's Title 24 has made progress on electrification as well. But to date, these overwhelmingly affect new construction. And that's kind of the easy part. In order to reduce our emissions by half by 2030, we've got to address existing buildings, and we've got to get on with that quickly. And today we have two of the leading thinkers and practitioners working on exactly that issue. First of all, presenting will be Barry Hooper. Welcome, Barry, to the AIA Big Coat meeting. Barry has been one of the most effective and influential policymakers in the field of building decarb. He's a senior green building coordinator with San Francisco Department of the Environment, and he's been a key leader developing San Francisco's building decarbonization strategies for a number of years now. While lots of people are thinking about and posting online about what we should all be doing, Barry is hard at work in the trenches actually getting it done. And the policies that San Francisco has passed, I just think are a model for the nation. And I'm so impressed with it, and I wanted all of you to hear directly from Barry, in particular about his work on existing buildings. And I think other cities can use this as a model to adopt. So thank you for joining us today, Barry. I'll go ahead and introduce Sean as well.
Well, I think someone's typing and we can hear, so I was going to encourage everyone to mute themselves if they could.
Thank you, Sean. Sean, welcome to our Big Coat Committee. Sean has been a force of nature in the world of building electrification. He is absolutely one of the leading thinkers and innovators and practitioners in the field. He is a tireless advocate that always seems to be there when building decarb is being discussed. Sean and his firm have designed over 10,000 all-electric residential units, 10,000 that is, new and retrofit, over 25 years of practice. Many of you have seen his excellent guidebooks that he's co-authored on how to electrify buildings, single family, multifamily, commercial buildings, new and existing. It's a great resource, and I highly recommend you check them out. I'll put a link in the chat here in a moment. They're free, you can download them. It's a go-to source of great information, and has really been effective in helping these cities pass their ordinances. So I thought that we would start with Barry, and then maybe we'd do some questions after Barry's part, and then we'll come back and kick it off with Sean, and then hopefully we'll have a discussion afterwards. So Barry, you can share your screen and take it away. Thank you.
Thanks, Scott. Can you see my slide well?
Yes.
Missed the opportunity to mix up my two screens. Great. Well, thank you very much for the kind introduction. And I'll look forward to living up to portions of it. But really appreciate the chance to talk with y'all about San Francisco's, particularly it's our climate action plan and recent activities and how that fits both into existing and the policy roadmap looking forward. When we look out over the next 30 years, it's helpful to start by looking back over the last 30 years. So San Francisco pegs its greenhouse gas emission goals against 1990, and that was rooted in then Mayor Newsom's desire to prove that the Kyoto Protocol could have been implemented just fine. And so over that period, over the last 30 years, the emissions from the operation of the entire built environment citywide have declined more than 50%, 50%. And that reduction has come definitely from efficiency, from both the efficiency programs, from code, from best practices in design. It has also come from cleaning up the sources of generation of electricity. And so as it stands moving forward, as is the case throughout California, but a little bit more so, natural gas is the source of emissions now, and that will just be stronger moving forward. And frequently, some of these slides are information that are unfamiliar to a lot of audiences here in San Francisco, that they could be familiar, contain information familiar to a lot of you. But one thing that is not common knowledge is California's electric grid is definitely several years ahead of the US, and that's critical to the importance of electrification. So if we look at all electricity purchased for sale to Californians in 2019, 46% of it was generated from renewable sources. And I'm using the term renewable a little generously here to include large hydro, as is the case because San Francisco benefits from a lot of large hydro generation, and it is renewable, whether the regulatory definition fits or not. If we look then to nationally, the same period, about 26% of energy was generated nationally from that same set of emissions-free sources. And when we zoom in on San Francisco, 83% of all electricity generation for sale in San Francisco, including all the imports and the different utilities that serve the city, 83% was generated from renewable sources, and an additional 10% was generated from nuclear. So the carbon content of that electricity is very low. So taking that into account and acting in response to the declaration of climate emergency by San Francisco a couple of years ago, the city's elected officials updated our climate action goals looking forward for the next 20 to 30 years. And that was part of it, was an acceleration. So they revised our goals to now aim to reduce emissions 61% by 2030 and to eliminate emissions economy-wide by 2040. There were a number of sub goals in there. I'm just going to hit a couple key highlights relevant to this talk, directly relevant to this talk. So we're aiming for 100% renewable electricity to be the norm citywide for all customers by 2025, and to eliminate fossil fuels in new construction as of last year in the largest existing commercial buildings by 2035 and citywide by 2040. The motivations recognized in revising those goals and the policies I'll talk about boil down to the health and safety of our citizens. The image at left is a fire and explosion on Geary Street a couple of years ago due to a gas line rupture. The health is well documented that approximately 23 to 28 San Franciscans die prematurely annually due to exposure of the incremental air pollution from combustion of gas in buildings. We look at resilience in terms of energy resilience. We think that the conversation is usually backward, that our ability to restore electricity service as a society is much greater than our speed of restoring gas service after the number one type of systemic risk that we believe we face, which is a huge seismic event. It was PG&E's projection that after a 6.8 magnitude earthquake, electricity could be restored to more than 98% of the city within approximately 1 week. And the same level of service for gas would take 6 months. And so equitable access to those resources is, of course, the last foundation of this effort. We need to bring along all of society and not just provide those health benefits to those who can most easily afford it. So in that context, been doing outreach for the last 3 years, leading up to the publication of the Climate Action Plan last month. And the Climate Action Plan, as you know, since it's a big city and those are big goals and there's quite a bit of detail to it, the Climate Action Plan contains strategies and actions. I'm going to just a quick overview of the major strategies are a transition to 100% renewable electricity, the energy supply, a significant effort to be inclusive in terms of workforce development and capacity and distribution of those resources, in terms of buildings, to eliminate fossil fuels in both new construction and existing buildings, but recognizing that in existing buildings, we're going to have to tailor our solutions to differing building ownership systems and use types. And the rest of my talk, I'm going to focus more on large commercial buildings, which have appeared to be the most complex type and the least focused on in most discussions of building decarbonization, because they're comparatively rare throughout the rest of the state. And in so doing, to focus on building decarbonization workforce development, particularly for our disadvantaged communities. San Francisco is not going to lead regulation of refrigerants to the best of my understanding, but we do have a role in advocating for effective regulation, educating the public, and you know, a number of things that are going to be essential for the effective transition of refrigerants. And the Climate Action Plan contains quite a bit of other detail regarding transportation and land use, which regarding the embodied energy and management of that in materials. And so I'll just refer you to the document for the gory details, but the most frequently asked question is that we encountered during public outreach was, you know, why doesn't the Climate Action Plan propose X? And the most frequent answer was, given this presentation, we had to kind of cut to a few key details and it's in there. So looking at the strategies, major strategies for built environment, again, it boils down to clean energy and eliminating fossil fuel use in buildings. And so the strategies in a climate action plan, if you haven't read one super recently, are really, you know, major direction and guidance, and the strategies are underscored by actions. How will those strategies be implemented? That's where the beginnings of the detail are. And San Francisco's Climate Action Plan is different than some. It is not a legally binding document. It is a plan for what sort of policies would be necessary going forward. So as a key example, in terms of addressing emissions in building operations, one of the actions calls for by 2024, San Francisco to adopt a policy requiring the largest commercial buildings to transition to efficient electric equipment by date certain, 2035. By 2025 to begin regular disclosure of their progress toward meeting that goal, and to allow some flexibility as well as to provide effective financial signal, allows flexibility about fees in lieu to delay electrification, where that would be a source of revenue for upgrading a low-income and affordable housing. And so I'm not sure how this goal sounds in this group, but you know, when sharing this goal, which was developed, and I'll explain how, in partnership with the largest real estate owners in the community. If you weren't in the room when this goal was developed, the most common response is, that's impossible. Like, how do we possibly accomplish that? These buildings are so large, the equipment is of a scale that just, you know, directly transitioning my gas boiler in building X would require massive new electric work, and the grid just absolutely can't handle this. Like, that's impossible. And so a key part and underpinning of, you know, why we do think it's possible is addressing those questions, starting with how. And so, you know, we've had the benefit of a lot of leading research. Of course, Sean will talk about the application of building decarbonization in real world buildings in our community and elsewhere in California. And that's led to a lot of, you know, the beginnings of design practice that clarify that it is true that we are unlikely to take, for example, a large and relatively rarely used a capacity boiler and directly replace it with a electric device that functions exactly the same way. Most likely you're gonna have to, it's a redesign challenge and opportunity. And so just looking at heating hot water, evaluating the path forward for a given system is becoming essentially a decision tree to figure out, you know, what, just because systems are typically designed for, say, 180-degree hot water at a particular volume, that is a function of, that's the typical delivered water temperature for a gas boiler rather than the only temperature that the given system can operate in. So you go through the practice of efficiency and load minimization, but doing so in a manner to ask how little change is possible in a given system before we can make it practical to make the transition to using a heat pump instead of a boiler. another major question is, who's doing this and where are there examples of these kind of crazy ideas in large buildings? I mean, in a home, it's one thing, but in a large building, this, again, we need examples to be able to move forward. And so the good news is that we do have examples emerging, thankfully locally and also nationally. And so 3 key ones in San Francisco that represent the a range of building scales. We have a construction underway at 188 Embarcadero. That's a building that happens to be owned by and occupied by Google. And so it was straightforward to be a early mover because alignment of ownership and occupancy does simplify negotiations quite a bit. The second major example is Levi's Plaza campus. So that's 6 buildings being electrified and totaling just under 1 million square feet. So really addressing the much greater scale and complexity. What's interesting for both of those projects is definitely for 188 Embarcadero and for the first 2 buildings that are where the designs have been completed and construction is proceeding at Levi's Plaza, there has been no upgrade necessary to electric service. So they've been able to reduce loads, electric loads elsewhere in the building, minimize the water temperature for systems that require heating, and in so doing, been able to figure out how to make the transition in a way that meets their design intent without any change to electric service, let alone a massive increase. Then let's pivot to SFO. So at SFO, you have famously the 4 major terminals, total 3.3 million square feet. They share one central heating and cooling plant, and that system is dependent on a legacy system is dependent on natural gas. It's near the end of its life. And so SFO has been in planning, and they, because SFO has set goals more ambitious than San Francisco as a whole, including getting to 0 emissions quite a bit sooner than the rest of the city. The upgrade of their primary point of consumption of natural gas is a huge opportunity. And so they've been looking at the central plant as an opportunity for electrification. But they had a major problem, actually a directly analogous problem to what you might face in your own home or what is faced in those other commercial buildings. And that is SFO, while it's a massive campus, it's served, it receives electricity via 2 substations. And it's important to the operation of the airport that those substations, that we maintain redundancy. And so each substation can operate at no more than 50% of capacity. And in summary, not being super precise, but in summary, those substations do operate at 50% capacity already with a natural gas central plant serving the major terminals. And so they asked the question, how can we get this done? How can we electrify the central plant? And we prefer not to have to redo the major electrical works for the entire airport at the same time. That would be a dramatic investment, to say the least. And asking that question, of course, turned out to be very helpful, and has led to a all-electric design that is the initial projections imply that the flexibility about when to operate the plant will actually yield a net reduction in electric load from the plant. So electrifying the plant the electrified plant is projected to have lower peak electricity consumption than the gas consuming central plant. And the reason, again, being distribution of the load more effectively over time. And so it is likely that SFO will be able to expand other electricity dependent services such as electric vehicle charging offerings through electrifying its central plant. And there's a kind of similar result that's been completed and built at the down at Stanford. Pivoting to the East Coast, a tool I'll talk about in a moment. The NYSERDA has been aware that the city of New York has had a policy, a directly related policy, Local Law 97, in place for a few years, and the initial compliance deadlines are coming up that will require emission reductions citywide across the largest building stock. And so their state regulator, the equivalent of the Energy Commission here in California, NYSERDA, is investing $40 million to help a big tranche of major building owners successfully navigate electrification to prove it can be done in a much, much more challenging climate than here in San Francisco. And so what NYSERDA did is they put up $5 million for design assistance in 2021, and worked with a total of 10 owners to develop pitches and proposals and designs for a subsequent tranche of funding to implement those designs across the building stock. So a total of $40 million will be invested in by the city of New York. And in the process, a number of lessons were learned from those pitches. So I'd just refer you to the bottom link at the bottom of this slide, as well as if you're looking for other examples of electrified buildings at different scales, since I'm really focusing on large commercial today. Electrifiedbuildings.org is a great resource if you haven't checked it out yet. So how then, is that planning succeeding in New York? That'll be what I'll talk about briefly in the remainder of this deck. In developing those goals to pursue and achieve electrification downtown San Francisco by 2035, we engaged the major ownership interests, BOMA, their major tenants, engineers over a period of months as part of the Zero Emission Buildings Task Force. One of the work groups was focused on existing large commercial. I'd refer you to the report for a lot of very interesting feedback that we received, but it boils down to this slide, that there was an importance of recognizing a shared responsibility that we do need to get decarbonization done. That's necessary to protect those buildings as real estate assets for their owners and to keep them meeting the tenants, both short and long-term expectations. And in the process, we need examples like I've been talking about. We need to recognize that there are improvements to technologies and particularly equipment availability and specifications that are going to evolve and do need to keep evolving. At the same time, there needed to be a regulatory signal. We needed to take away the question of whether we'll decarbonize and move the discussion to when. And so that was really the request from building owners to have a clear signal that they would have to get it done, and the date was set. Was suggested by them. We asked what would make sense, and the balance that they suggested was climate change does present an emergency. At the same time, their existing investments and investors, they have legal obligations to them. So if we set a date that was too fast, they'd be unable to act. And so we needed a horizon that was beyond their current capital planning, but still represented the urgency of the matter. And so that's where 2035 came from. And we need to recognize that those large buildings, they need a plan for improvement over time that recognizes opportunities will arise over this period. And we need to leverage their existing process of investing as well as some additions. And then people need recognition, particularly because environmental and social governance investing is a key source of capital for the largest commercial building owners and a large chunk of course, real estate. And so they're looking for credible recognition of success that they can share with their ESG investors. And so just diving into one component of that, the observation was it's important to build upon their existing cycle of real estate investment. So to look forward in the future and figure out when there'd be engage engineers and the ownership to figure out when there'd be opportunities for a given building, what are the likely policy triggers and future needs of the building, and can we plan for what a building should look like in the future and work backward from there. So they're looking for support for planning and execution in advance to eliminate missed opportunities. And so this is really the large buildings version of you're going to need it in your own home, need to know what you're going to do when your water heater fails, if you have a gas water heater, if you want to successfully transition to heat pump. And so in anticipation of that question, we've been working with Arup and Ember Strategies with initially some funding from the Energy Foundation, which we're grateful for, as well as an investment of strategic energy resources funding from PG&E on a method to really evolve energy planning and energy audits in particular to support this mechanism, and really to recognize that if we look out in the future, we're going to have to be strategic at the individual building level and facilitate a discussion, an iterative discussion between the engineer or engineers and the building ownership and decision making to fit decarbonization within their existing processes of decision making and investment. And so the core of that's looking out in the future and recognizing that the notion of payback is irrelevant. Rather, we need a baseline. We need to recognize that there's a baseline of, if you take no action, there's a cost to that, and to give the engineers standardized tools for assessing what that cost of inaction and reacting to future, likely very stringent decarbonization policies would be, to then compare that to say, what's a absolutely optimum scenario for improvement and maximum efficiency, and then to have that to be the basis of discussion for identifying opportunities that are more realistic, that are probably somewhere in between those two poles. So I just want to make a distinction, two distinctions, and I'll pause for Q&A. This is fundamentally different than an energy audit. So a strategic decarbonization assessment is still the application of the engineering know-how that's exemplified in an energy audit, but we're asking a different question in an audit, such as those that are required currently in San Francisco on every 5 years for large buildings. What we're really effectively implicitly asking is, what could you do to improve a bit today? How could you reduce your wasted utility costs? And what are the smallest amount you could spend to do so? And we're asking a specific audience in the building those questions, essentially the facilities manager and others who are directly responsible for engineering of the building. And so all of that favors the type of conversation we're, I think, all used to, and there can be some frustration with that favors short-term thinking. For planning for decarbonization, what we're aiming for is a discussion with the asset manager, recognizing that just the budget for flowers in the lobby in some of these buildings can be greater than some of the maintenance budget. So really looking at what's necessary to protect this building and to ensure its viability as an asset, and how should this building perform in the future, looking backward. And then a last key point is this type of assessment is really meant to be and depends on, and it's can be quite a challenge for the practitioner, shifting from attempting a cost projection that is accurate to providing multiple scenarios that are reasonable. So we're looking for order of magnitude costing in a decarbonization assessment rather than specific financials. So with that, I'll pause for Q&A, talk a little bit about the city's plans, and then moving forward, what are some of the tools we've been developing to put those into practice.
Thank you, Barry. That was super informative. Any questions?
I have a chance to ask. Barry, what I was surprised really, it was just how fast and hard San Francisco is moving. You'd named so many different policy initiatives, actual practical projects, that was comprehensive and impressive. So do you think that you'll go faster than your actual targets or slower? I mean, are you going to beat
oh,
your
sorry,
goal?
the way you asked that, I thought there was a follow-up.
I'm curious. Yeah, do you think you're going to succeed? How's it going?
We're so the plan really was finalized last month. So we're definitely on target thus far. I do think that it's a good question. So we do expect to be on target. The a key question actually is going to be which policies are going forward first this year. And this is a couple things are just absolutely clear. One is, we have a triennial code cycle in California. And so I do get to pleasure of working on the commercial initiative that I was discussing, but I'm also responsible for carrying forward San Francisco's existing requirements and making that fit with the changes to the building code. So that's on the agenda. There are also a number of residential policies that are likely to be led by others, but I'll be supporting in the next year. So I think that's more likely what you'll see directly proposed is the details a little finer than what I covered today. And I do think you'll also, in terms of large commercial, the ball is partly in the office, in the mayor's office's court. And I think I expect to hear from them sometime in the very near future about this, so that it would represent some renewed momentum moving forward. So I'm sorry that in other words, it's hard to answer because it's there.
Well, I mean,
it's theirs to kick off. Yeah.
Yes, but that was actually, I was trying to get a sense of at a practical level, your next steps and how likely you are to succeed. There's a lot of chatter about whether or not we're going to, in California, make our deadlines by like 2060 at the current rate that we're working at. And San Francisco is so much more advanced than the whole of the state that I am, as on a daily basis, I'm sort of checking in on how bad our crisis is, yeah, in terms of our policy development and our actual changes that are happening out there,
When we first drafted the plan, it was against a 2045 deadline, and so that was one of the wrinkles that the policymakers put in at the very conclusion, was that didn't fit the problem, right? And we needed to ratchet it up to 2040. That adds some complexity. Embedded in the detail there about 2035 is that fee. So I do expect some buildings not to have fully completed that transition at 2035. And I expect there to be some revenue. And so a key question actually be when those fees begin to be collected, because it doesn't mean that you wait till 2035 before having a fee. So that's a key question. There's a lot of detail to work out in that policy.
Right,
in
those are the
2023.
I see there's 2 questions. Keith, you're first. Do you want to ask yours?
Yeah, great. Oh, thanks so much, Sean. And Barry, thank you for the presentation. Really, really exciting and interesting. One of the items you had on your list was the equitable decommissioning of the natural gas utility. I was curious, how far along are you in those conversations? And could you just give us a glimpse into what that process actually looks like?
Sure. That really is the set of policies or activities that are envisioned there are recognizing that the primary regulator of the gas utility is the state, of course, particularly the California Public Utilities Commission, that the Public Utilities Commission is entering a iteration, a phase of a proceeding to ask, how will the state set up appropriate rules for the disposition of gas assets moving forward, to recognize that there's some things need to change for it to be possible for the state to meet its goals. And so that set of activities really is meant to recognize that cities have a role in that discussion as well, that whereas the state does set the rules and the utility does both make the investments and manage those works, we're kind of missing in that conversation that cities have a implicit role in utility infrastructure design and maintenance, through land use planning. So where construction is located, the scale of it, its uses, and what fuels are allowed, those all heavily influence the gas system, as well as the notion that gas, for the gas system to shrink and for leakage from the gas system, which is a critical issue, to actually diminish, we need concentrated decarbonization. And that's also essential to the economics of the gas system. And so it's also recognizing that it's pretty hard to imagine the utility doing a better job than a local government in terms of engaging the local community systematically and prioritizing to local community needs. It's pretty tough to imagine state regulators doing that simultaneously across all of California. So, local governments have a role in participating in that. It's just basically a placeholder that we need to assemble key local context and enable this as a land use process.
So why don't we do one more question from Dave, and then we'll turn it over to Sean, and then we'll come back to Q&A after that. Dave?
Great, thanks. Quick question, Barry. Awesome presentation, really appreciate it. Could you talk briefly maybe about how you guys have looked at demand flexibility as a key enabler for decarbonization technologies, particularly with renewables at such a high percentage being available at variable times, and how especially some of these large high load customers are going to be handling things like thermal energy storage, battery storage, and other strategies like demand response?
Sure. Well, so one good layer is that whenever I end up being the person engineering a building, we've all failed, right? So try to work on at the policy level. So those are important questions, but I hear most of that is, do the rules actually favor management of that asset in a way that reduces the likelihood of the need for upstream investment in the utility grid? And it seems like there's quite a healthy discussion favoring that, as well as the rates themselves. So another way to put that is the reason I talked about those 3 scales of project and mentioned a house is I actually think as all Californians, as much as possible, the question isn't exactly how do we function in a way like that uses utility jargon, but rather how do we use our existing electric service as effectively as possible? How do we avoid upgrades? And the answer, of course, is primarily efficiency. And the more, of course, lots and lots of conditions will require electric service upgrades, but the more individual projects of any scale that sharpen their pencil and look at how they could minimize or avoid upgrades, the less their maximum peak demand there can possibly be, and so the lesser investment is needed in the grid. To put that just a little more precisely, the SFO is a practical example of massive application of what I hope Sean's going to talk about, this Watt diet idea, right? That yes, it is all the engineering jargon is necessary to enable that because it's such a big, complicated system. But essentially, we've got to keep peak demand no greater than it was before and still achieve our design intent. And so that's the theme I see. I see that as very, very critical in San Francisco because of the expense and complexity and timing of digging up urban streets. If more projects are dependent on major changes in electric infrastructure, the slower the overall electrification is going to proceed. So hope that addresses your question. Is I don't directly plan to be involved in the demand and management side, but all the rules have to favor that. And then we need to make sure that the owner and operator are aware of those rules and have the financial incentives to take advantage of them.
So Barry, thank you so much. That was super informative, and I hope you can stick around in case there's more questions later. With that, I will turn it over to Sean. Take it away, Sean.
Hello. Hey, y'all. I'm just making sure I've got that power efficiency Watt diet slide there. You threw me for a loop there, Barry. Okay, let me share my screen. Here we go. And I'll make it full screen. Hey, everybody.
Got it? Yep.
All right. So this slide, the intro slide, is to just show you, hey, all over the country, been going on for quite a long time. People have been electrifying commercial buildings, hospitals, universities, public schools, large military complexes, clinics, the rest of it, all over the country. So just to know that this is not a California thing per se. Actually, many other parts of the country have gone much faster because of our gas-friendly code, gas promoting code since the energy crisis of 2001. I put that in quotes because you recall that was a scam that Enron led. So I have been in the energy scene since 1995, and so I have a lot of stories that I can add to this as a student of it. I started at HSU studying building electrification in 1995 at this demonstration house from the Carter era that's still there today, the oldest demonstration house in the country of how to move towards renewable energy, including electrification. Then this is a nice example of little affordable senior homes that have supported, working on about 300 affordable housing developments. The bottom here is an example of my crown jewel at the moment, this 500 unit mixed use, there'll be a Starbucks, etc. Resiliency with batteries and 9-story tall solar on the parking garages, and it's starting construction. It's delightful. So mostly I work on affordable housing, to be clear, but we're going to talk about commercial today. Just going to say, it reemphasizes this is not new. This is from the 50s and 60s era when the utilities, about 1,900 of them, banded together for an advertising program as they rapidly electrified gas loads. And that went until 1963 with the oil embargo. So there's a lot of legacy buildings that we can talk about from that era, and also parts of the country and parts of the world that didn't have easy access to natural gas, just a lot of the world actually. So here's an example. Is this just a California thing? No. This is Hong Kong, for instance, a part of China, but it has been in many ways sort of locked away from access to fossil fuels because of the political issues. And the country, and any time that you're sort of, physically isolated, it's just easier to put in electricity. It's always the easiest utility to put in. So this is a nice all electric office tower there. I got notice of it because they'd actually retrofitted the electric resistance boilers to heat pump boilers about 8 years ago. And so it's just part of a list of projects I was reviewing. I was like, oh, this is a nice one for this presentation here. Here's another nice example. Hawaii, an island state that doesn't have access to fossil fuels except what is boated over. Interesting is that in Hawaii, you see the story, first of all, like this is where Elvis loved to stay. And actually, is that well, Elvis did love to stay, and I don't think it was at this one. I think it was the Hilton. And I don't have the slide of it. I have it in a different slide deck. The Hilton is pretty cool. Anyway, Hawaii didn't have access to fossil fuels. Then they boat over fossil fuels and they turn it into a natural gas-like material, similar to what's called city gas, which got eliminated in most of the world around in the 1970s. It was a very easy way to commit suicide. Huge drop in suicides in Britain. Very obvious as they got rid of city gas. And like Sylvia Plath killed herself by putting her head in the oven. It was a very painless way to die. Natural gas is a different set of compounds, doesn't have carbon monoxide in it. It, of course, creates it. So anyway, Hawaii, a lot of it was built all electric. Easy to do. It was difficult to get the pipeline of the city gas, which is still what they have. They don't use natural gas per se. Here's the Ritz Carlton. I just want to emphasize that, it's most of the fancy hotels in Hawaii are all electric. Here's their little induction. They've got some big electric boilers, etc. Then I want to say, but have you heard about block power? They're all over the US now. So on the left-hand side, you can see one of the public buildings that block power electrified in New York City. That's where Don Albert, the CEO, started, essentially in 2011. And he has succeeded in getting Wall Street financing to grow his company quickly, expand across the country. And so they're in conversations with now dozens of cities to do what they just pulled off in Ithaca, which is they got the agreement that they would be the project managers of electrifying the whole city. And NYSERDA put in, and others like the city put in money and some grants. There was a whole chunk of money that was put into a separate account to buy down the risk of non-repayment for these non-secured loans that people are taking out to electrify their homes. So that reduced the interest rate down to almost no interest because there's no risk really associated with it, with taking the loan. The city already has the whole non-repayment fund right there. So when people fail to repay their unsecured loan to electrify the building. So, they're going after the downtown, of course, and that lovely downtown in Ithaca, the hometown of Cornell, but they're also in conversations with Milwaukee. And I hear they're over in Oakland and. want to emphasize, like one of the main things that people wonder about is can commercial buildings in cold climates work out, like up in Shasta or Truckee, or in this case, up in Alaska, the Sitka Public Library System. And yeah, they got rid of their expensive, difficult to work with fuel oil, which is diesel fuel, and they put in a VRF called variable refrigerant flow. It's a big heat pump. It sends out a big tube of refrigerant to a manifold, and that's the main thing about it, is that the manifold then spreads like a little octopus of smaller refrigerant lines to go to like duct work or radiant panels or whatever is the actual heat distribution or experiencing part of it. Anyway, so they put in a big old VRF. So it's a cold climate heat pump, and that's how this Alaskan library is heated and cooled. Our hard rise is hard. I didn't expect that to be hard to say. Our high rise is hard. Nope. This is renamed after an architect, Arthur Erickson. I thought you guys would appreciate that as architects. Arthur Erickson developed this. It's a cast concrete. It was great advances in concrete to make this building as one of his favorites. So they renamed it after him. It was built in the 60s. And here's the gas boiler. And here's now the hot water storage tanks and what's called a swing tank, because heat pumps usually need more storage because they don't have as much instantaneous capacity. So here's the heat pumps down there. These things are all collecting heat from the air and stripping, so it's chilling the air. Usually, like if it's down in the basement, you might duct air to the heat pump room or put it up on the roof. And these are carbon dioxide heat pumps called SAN CO2 heat pumps, carbon dioxide heat pumps. They work to -30, -40. They heat water up to 150 to 190. I'll show you another example in a sec. Now, getting into California, let's show you the world. They're giving you little stories about why the world is the way it is. Lack of access to fossil fuels, the fact that it's cheap infrastructure. This is why actually all electric construction is the dominant form worldwide, because most of the world doesn't have access to fossil fuel infrastructure like the United States. It's expensive. And America does expensive well. So here in California, this is 87% of the commercial HVAC systems, and the individual percentages are seen here. 59%, these really simple packaged unit single zone systems, which is why Stet Sanborn over at the Smith Group, who I consider, it's impolite to say who's the best, I guess, but he is absolutely one of the best and totally my go-to. And he's been doing cold climate systems all over the country for Smith Group. So he's a person I felt like had the most experience of working in Minnesota and Wisconsin, where I'm from. Okay, so as he says, the biggest market, if you want to make a move on actually getting gas out of commercial buildings, is to target the rooftop package unit with easy retrofits. You take one package out, you put another package in. Slightly more complicated though is the 13% of them that are split systems, because frequently you have to replace essentially everything. The system that's up on the roof, then the line of refrigerant that goes to the fan coil, which is this box here. This looks like a ducted system. Okay, then unit ventilators or unit heaters, that's about 8%. So like, for example, SoCal Gas, that's the irony, down in LA, they've got like a 50-story tall building. It's all electric, except for their restaurant, which has like 1 stars, where people have complained about getting sick there and seeing rodents. I'm not joking. You can see some real trash talk about the Blue Flame restaurant in SoCal Gas's tower, but the rest of the tower is using unit ventilators, using like just electric resistant strip heating in the office building. And then there's these packaged thermal heat pumps, 7%. So this is 87% total. These are the things that you need to look at how to electrify as you're doing retrofits. There's a little bit of other stuff, but like for instance, 6% are doing multi-zone. So higher end developers and universities are absolutely 100% on board with electrification. No question about it at all. This is John Gautry over at Integral, great engineering firm. So for the 6% that are this, slightly more complicated systems generally, but they're big systems. They deliver either refrigerant or hot water. one of those two, on cold water, cold refrigerant, cold water, hot refrigerant, hot water. Either of those two essentially are being delivered around the building to systems that then just take the heat or the cold and blow it or chill surfaces, etc. But this is yeah, totally doable. Just wanted to say this is the multi-zone. Now, what about variable air volume systems? This is where you might have, like, this is the Vancouver City Hall. In Vancouver, they craned in this air mech here, and it's sending hot and cold water around the building. And then it's delivering to these boxes. So this is the hot water, cold water version of a box that's a variable air volume air distribution system. Basically takes air, and it has this damper. You can see that fold of metal there, and this little computer here that's controlling the amount of air that's leaving it, so that you can essentially have different rooms have different zones. This is a way of zoning the heating and cooling, where you can have a remote control and set the temperature in a different area. Now, this is very energy intensive and very common. This electric resistance doesn't have air conditioning. This electric resistance version, though, if you're just doing heating, like you frequently have in clinics where you pull in outside air. Anyway, this is more energy efficient. You might be surprised, but basically delivering heating and cooling through a building's walls instead of delivering electricity is way more energy intensive. You have a lot more heat and cooling loss too. About half of it is gone by the time it gets to the place you're trying to use it. It's just gone from loss through the piping. So in retrofits, one of the things to look at is that would it make sense to put in just simple electric resistance variable air volume boxes like this, as opposed to delivering hot and cold water like you have over here, because it's just half as much energy. Here's a nice little case study. These are the crummy old systems that were on the roof, and the numbers here, unfortunately, I can't read because of the. Okay, there we can go. So on the left there, they had 43 tons of heating and cooling. The ton is 12,000 BTUs per hour. So 43 tons. And it was replaced with this system. This is a VRF, so variable refrigerant flow. It's sending refrigerant in little tiny pipes around the building in a variable amount. It's got little computers to control how much it sends. So it put that in, that's 18 tons. So less than half is what they put in with these are heat recovery ventilators. So they recaptured a lot of the heating and cooling as they're doing the ventilation work. That's how they cut the tonnage in half. So they put in some efficiency. So just getting the heating and cooling back instead of having to make it new. So, and this is a good example of how this retrofit from, like, 1960s equipment going to modern equipment and modern strategies can create electrical capacity for electric vehicle chargers in a retrofit, for putting in a heat pump boiler instead of the gas boiler that's there. All those things are possible during significant, like, gut retrofits, which is a lot of the commercial retrofits. And the question, can you go in when you're doing that gut retrofit and electrify without increasing the service? Mostly yes. Ted Tiffany of Gutmann Blauvelt, we interviewed him specifically on that topic, and he was just giving example after example of how they electrified everything. And it's just because they're using modern, efficient equipment, even though they were getting rid of gas. And ostensibly, you'd think you'd need more electricity. But nope, just efficiency. Just modern design and efficiency did the jobs. Now, what about replacing big boilers that are doing 180 degree Fahrenheit hot water? A very common strategy in, like, buildings in New York City, where they've got radiators everywhere in all the buildings. This is for that. This produces 185 degree Fahrenheit water, just straight off the bat. It's a carbon dioxide heat pump. I mentioned that earlier, that it works to -30, so you can have a polar vortex in New York City or wherever you're doing your awesome architecture work. But this is a cold climate solution, and really any climate solution. It's doing terrific work, but it's just very resilient. You don't need to worry as much when you have one of these. It's a Link product by Watts. It's actually a rebrand of a European product, and these are all over Eurasia. Not just this manufacturer, many, many, many of them from the Pacific Ocean to the Atlantic Ocean, one continent of awesome big heat pumps, many of them using CO2. We just are babies in this stuff in the United States. We barely have any products compared to the rest of the world because since Ronald Reagan came into office, we've been heavily focused on energy independency as like a military solution. And that meant fossil fuels to a lot of our political, technical leadership for too long, unfortunately. So anyway, the United States is kind of unique that way. Most of the world is already much further along, for real. Here's an example of a manufacturer out of Canada using a different type of refrigerant. Maybe you don't want to work with CO2 and you want more manufacturers to play with. Okay, well, what you need is 2 heat pumps. One is a heat pump that goes down to say -30 Fahrenheit degrees. Totally can get that. This little green arrow here is pointing at -30 Fahrenheit. So you get a primary air to water heat pump that's for cold climates, -30. And you raise that water up to about 80 degrees Fahrenheit. That's over here is the temperature of the water. These little loops represent the loop of thermal performance for this heat pump. So you're going to get it at -30, but raise it to 80 degrees Fahrenheit. It can do that job. And then you can take that 80 degree Fahrenheit water, which this product is happy to work with, and you can raise it up to 180 degrees Fahrenheit. And this is a water source heat pump. So it's concentrating the heat. That's all. It's not making new heat. It's just squishing it into a smaller volume of water, which raises the temperature. So using a water source heat pump paired with an air source heat pump is a way of using all the normal quote unquote refrigerants, R410A basically, and R134A, which are getting phased out quickly, just so you're clear. The products are already out on the market and there's already all the regulatory framework to phase them out. So just, you should get familiar with CO2. Here's an example of how they're using an air source heat pump to heat this outdoor swimming pool at the Tamarack Club Slope Side Hotel in Ellicott, New York. It's a big resort, golf courses all around it for the summer and the fall. And you ski literally up to the swimming pool. The hills and the lifts and all of the rest of it take you right up to the hotel. So you can get out of your snow gear and jump in this hot tub, which is heated with a water source heat pump, pulling the heat from the swimming pool. And they've got that sized appropriately. So you have an 80 or 85 degree swimming pool that you jump into. And it's essentially being chilled by the hot tub, but that's fine because you're still pushing the right amount of heat into the whole system for that to work out. So you can see there's 2 outdoor hot tubs here and a big steaming outdoor swimming pool for the skiers. And aren't they lucky? On the other side, this is in Hawaii. So this is a community swimming pool. It's kind of famous for delivering a lot of Olympian swimmers to the United States. And this has got the Big Bopper from AquaCal. That's this heat pump up there. The Big Bopper are 500,000 BTU heat pumps. That's actually the same size as the Link. This is a 500,000 BTUs per hour heat pump. So you get one of these big blocks and it's heating water for swimming pools and hot tubs and such, because the water source heat pump would work that way. That's the best way to get your water up to like 105, 110, that kind of thing, when you're working with swimming pools and hot tubs. Now restaurants. These are 3 Michelin star chefs. So right here, this is Grant's Ashet's. This is in Chicago. Alinea is a 3-star Michelin restaurant. And he's saying within his all electric kitchen, technology becomes a very powerful creative tool for us. It gives us more ways to manipulate the food in unexpected and new ways. It becomes a creative outlet for us. Electricity is way more versatile. I can have a whole other presentation of it. You can just do so many more things and use it in such more controlled ways. Like sous vide, where you take like veal and you put it in a plastic bag and then you heat it exactly to 150 Fahrenheit in a tank of water. That's something you do with electricity. It's not safe really to risk what you're trying to do with gas, which can put the wrong amount of heat in more easily than electricity, which can be very accurate. Or here, this is Heston Blumenthal, just outside of London. It's a big deal restaurant. He redid his entire kitchen. You can watch it on YouTube, and he just goes on and on. I never thought after 20 years I'd be standing in a kitchen like this. It's absolutely amazing. You see this cool little thing over here on the right-hand side, the what is it? Gaseous CO2, frozen CO2 that's like turning into like a vapor looking thing. Anyway, It's pretty fancy. You can go enjoy his stuff. There's lots of YouTube clips. Or this fellow who has brought back the Bocuse d'Or, like the best baker in Europe award, to Belgium, I'm sorry, Denmark, pardon me, over and over and over, and also his apprentices. This guy is internationally famous, huge deal. And he says, I designed the kitchen myself. It's a gastronomic theater. It's very open, so we can meet the guests and they can see that we enjoy our work. I could go on into depth about this. Cooks, chefs, they don't like working in gas kitchens because A, they get a lot more burns, and B, it's hot because gas just generally it's only 25 to 35% efficient versus electric resistance at 65% and induction at 70 to 90%. So therefore, they have to put twice or 3 times as much heat into the kitchen in order to get the same amount of cooking done when you're working with gas. It's just hot, really uncomfortable. So, you know, these folks are not trying to sweat in the food. Here's America's test kitchen chefs at home. The COVID crisis meant you got to see all the chefs in their own kitchens, and you can check out their induction ranges in the background here. Jack Bishop is the chief creative officer at America's test kitchen. And that role of saying, like, I'm the person who knows how to do all the fanciest, most interesting, creative, crazy stuff. That's what you'd want to do on induction with the high-end piece of like really high controllable equipment. Not just like trying to figure it out with the gas flame, you know, like, oh, that looks like the right temperature. Here you have it in New York City. So this is what retrofits. If you're going into an existing storefront in New York City, or for that matter, San Francisco, the challenges of where you put the kitchen in an existing non-kitchen storefront are a pretty big deal, because you might have to disturb historic materials to put in venting for gas ranges and such. They take a lot of exhaust, whereas an electric kitchen, you can put in 2 pieces of cooking equipment and not put any venting in. So you have like a two electric devices allowance, and you can do tons of cooking with 2 things. So here, I mean, you can also do reduced ventilation with once you get to 3 and 4. So Wallflower, nice little cafe, Frankie's is putting out the noodles. Rucola, you know, one of those nice expensive burger places. Little Sheep Mongolian hot pot where they bring out your own induction hot plate in front of you, and you get to do all your dipping and such for the Mongolian dippable foods. Grand Army, super fancy, you know, seafood. And Sola, which does induction woks. That's what that chef is standing in front of there. That's a sunken in wok. So I'm trying to say, you can do it. This is the right way to approach commercial buildings, is don't try to put in gas and wreck the historic fabric of the building and increase infrastructure costs, et cetera, et cetera. Get fancier electric equipment, much of which is power efficient and can do multiple tasks. So here, Panda Express, they've got like 2,000 restaurants owned by this couple here, and they own them all personally. They're not franchised. And so they're going to induction warmers because they have way more control, and it doesn't use a ton of water, the way gas that's then heating up a plate of water that's then heating up the food is not very controllable and water intensive, messy, and kind of dangerous. You can get boiled on it, the water. So just go into induction, eliminate a whole bunch of messy steps. Or Benihana, Japanese steakhouse, they're the ones that are famous for doing the decorative, like playing with the food and throwing and juggling. That was something that was done in Japan after World War II to entertain American soldiers. And they were trying to like bring people into their restaurants, American soldiers there, because after World War II was a huge amount of financial struggle. So this was an inventive strategy to essentially get American tourists into Japanese restaurants. And then they brought it to the United States and turned it into like 130 restaurants around the country where you can see this amazing act of juggling and salt and such. Well, the planchas, the teppen, there's the same thing. Plancha and teppen are the same kind of device, a really hot surface you cook on. When it's gas, there's a lot larger chance of having an actual fire. Like they do fun fire, like this flaming volcano of onion rings. But when you have a bunch of oil around and you have for real open flames, it can be less than fun for the people who are standing or sitting around for this nice, birthday dinner. I got to go to one of these like on my 9th birthday. I loved it. Here's fireplaces. Let's say you're in the Castro district and someone would like to put in a bar or a lounge or something. These fireplaces are working either with LEDs or with halogen lamps. And if they're the LED type, you can make rainbows of flame. And the flame is mist, but is absolutely convincing. I turn on every night in my house. I have a little tiny house. I'm recently divorced, and so I built this tiny house for myself and tenants, and it's a lovely little building. And I have this cute little fireplace. It's a mist fireplace. The kids come in, we hang out around the fireplace, and they can stick their hands in it without catching on fire, but it looks like flame. So putting these into hotel lobbies and such, these mist-based fireplaces, it's also less expensive, lowers construction costs. You don't have to vent it out. You don't have to bring gas in. It's usually just either you directly plumb water into where the ultrasound vibrates. You can't hear it, don't notice at all, but it makes the steam. So either you bring in a water pipe, or there's just a tank of water that you just refill. That's how mine works. It's super easy, fully worth it. Runs for many, many hours. And this is for residences, and I'm making a calculator with my staff. We spent a year on it, how to make the National Electrical Code for commercial and multifamily buildings. But I want you to see how this would work in a house, something you would probably all have, where different types of systems use different amounts of power. This is all wattage. This is all trying to meet your space heating needs. But a 1-ton portable heat pump versus a permanently wired mini split doing the same job, 0 versus 1200 watts. Or a 3-ton system that's a mini split, doesn't have to blow air, so it's less wattage at 4,000. But that same 3-ton system that does blow air around, a central ducted system, 5,500 watts because of the blower. And what if you didn't get a cold climate heat pump and you just use electric resistance? Well, below, say, like 20 degrees or 10 degrees, as opposed to getting a negative 30 Fahrenheit product. Well, then this electric resistance doubles the power demand. So in the commercial retrofit guide that we're publishing, hopefully next month, we're a little late, we're putting it out. We have a whole product guide for cold climate heat pumps of all types, the package types, the hydronic types, everything is around its cold climate rating. So we can avoid this really big hit on the power demand of a building, which is using electric resistance when you could use a heat pump. And the same thing goes for water heating and cooking and laundry machines, say for a laundromat. There's so many ways of pursuing power efficiency if that's the issue. And since there's this unpleasant conflict between PG&E and the San Francisco PUC over infrastructure upgrades, when you are electrifying an existing building, it'd be really easy for everybody if you didn't have to ask for a larger transformer. For time, for money, for just sheer emotional frustration, all of that, engineering designs. So power efficiency, which just comes from better design and better equipment, is something to study and work with your electrical engineers on. Don't just accept this, that, oh, you have to put in this big of a transformer and it's going to be this long and hard. You can go back to the drawing board, so to speak, and say, oh, no, I want a cold climate heat pump. I want to think about this more carefully as we do blah, blah, blah. So anyway, now I'm going to show you a cute little video. Oops, sorry, this is not hyperlinked, so I'm going to have to escape and then copy. Apologies. I'll get this going in just 1 second. Putting in the video. Oh, now I'm going to reshare so that you can see the screen I want you to see. Okay, and I'll make it full screen. Yeah, full screen. Okay, so this is Japan. This is an advertisement. It's advertising how this Nissan Leaf can address a power outage. All right, so this is like a 30-second little story here. Oh, the power's out. The weather sucks. Let's plug my car into my mini mart.
Wow.
And the ice cream doesn't melt. Okay. So this is real. I'm going to show you, get back to my slide deck here. Keeping the ice cream cold in Japan. So they rolled out Nissan Leafs to be able to charge buildings in 2011. It started in 1994, just generally out there as a technical strategy, using electric vehicles to back charge buildings. Nissan made it official with some products after the tsunami in 2011 shut down essentially 1/3 of the nuclear power plants in the country, or 1/3 of the power plants, all of the nuclear power plants in the country. And so Nissan had an electric Leaf, and they made these sort of suitcase-sized devices that would invert the power from your battery into your building. So this is coming out in a big way this year, pardon me. This is the Ford F-150 Lightning, which just doubled their production this year because of outrageous demand that people want the electric F-150, the top selling vehicle in our country of all vehicle types. And this has 11 120-volt plugs and a 240-volt plug. So you can show up and power the entire construction site. So you can power your house after a power outage. So you could power a building, a commercial building. You could power the community center. This is a big battery. This would be the biggest battery of any vehicle that's out. The F-150 Lightning with the extended range and comes with the vehicle to building charging. So if you're thinking about a Tesla Powerwall, that's 13 kilowatt hours. This is going to be coming out, it sounds like, with 200 kilowatt hours in the battery. So we're talking like 16 or 17 Tesla Powerwalls, and you can just roll this thing up when you need to use it for power outages, as opposed to having to buy a massive battery that sits on the side of the building for resiliency purposes that never gets used. And you could actually plug in maybe more than one car. You could go get the car charged up someplace else and bring it back to the community building. We've seen this in 2019 when there was a gigantic typhoon, a hurricane in Japan, knocked down gigantic transmission lines, and there's millions of people without electricity. And Nissan started allowing Leaf owners to come to their car charging, to their car distribution places and charge up there, and then bring their car home to charge their house if they're inside this multi-million-dollar corridor, a multi-person corridor of no power. So that's been going on now. This is real. In other countries, people are already well into this and can respond to crises with their own electric vehicles and leaving the area and getting powered up and coming back as the way to do it, as opposed to, say, getting a generator, which, you know, nearly lit my grandma's house on fire because the neighbor's house did catch on fire when their generator in a power outage up near Seattle, you know, they're using a generator, caught their house on fire, almost burned down grandma's house. That stuff's dangerous. When we had a power outage up here with a generator, it burnt down a quarter of our downtown. This is just a few years ago. A whole city block of old wood buildings all got a fire underneath them from one restaurant running a generator. And it shut down that whole city block of awesome, beautiful old buildings. So can't emphasize enough, this is a lot safer and more convenient and cheaper. And all of VW's electric vehicles in 2022 come with this capacity, not just like the extended range F-150, all of them. So it's my last slide. Back to the story. This is, you can live better electrically. It was the catchphrase of Ronald Reagan back when he was the spokesperson for those 1900 utilities and had the #1 television show on Sunday nights, the General Electric Theater. We have Schwarzenegger still making news. He has a great editorial in the New York Times opposing the CPUC's $50, $60 surcharge on homes that have solar on them, which is totally a gift to Wall Street that owns PG&E, and SoCal Edison and the rest of them. He says the biggest evil is fossil fuels. It's coal, it's gasoline, it's the natural gas. And not too many people are allowed to touch Greta Thunberg, let alone like hang out. The two of them are genuine buddies, and I trust those two more than most people. And then there's Gavin Newsom saying, this Adobe tower represents one of the cleanest investments that's ever been made, an all-electric tower. And our first booklet that Scott mentioned and helped out with in 2019 was a guide to commercial all-electric construction to help Adobe. That they're like on the cover of a book, they had a schematic designer like, this is for you. Please electrify this building. Here's technical strategies. And they did. And that wasn't just us. Like there was a whole effort to try to get Adobe, and we were helping, right? So now this summer, you know, right after he was making his emergency declaration of drought and such, he went in front of this building to say, like, this is a big deal. This is where we're going. So with that, it's time for questions.
Thanks, Sean. That was fantastic. Really appreciate all that, and always something new every time I watch one of your presentations. So thank you.
You're welcome.
Questions, anyone?
Let's see. What time? Did I go way over? How bad am I?
I'm sure we got some questions. We just got to give people a chance.
Ismar likes,
Um,
thank you for sharing Arnold's opposition. And it goes back to your first question. So Ismar, I'm going to go to your,
Oh, I see Paul has a question, has his hand raised.
okay.
Hey there. So you were talking about retrofitting some large buildings, and or maybe it was Paul Cooper before you, Barry Cooper, talking about that. But I was working on a project that's 30,000 square feet that had a four pipe system running through it.
Yeah.
And my engineers are fairly savvy, and we couldn't find a boiler that would be non-gas that could replace the existing boiler and meet the specs without swapping out all of the equipment within the building.
This one is new.
So these are brand new that just came out that are all electric.
Yeah, in the United States, this is new. I mean, it's
Awesome.
an old product over in Europe, but linked by
Yeah.
Watts. This is what I think you need. It's the 185-degree Fahrenheit, 500,000 B2 boiler. And I believe it can also do air conditioning in reverse. So yeah, and the other big actors I've seen is Transom has been willing to put together big systems, but they're out of Canada.
I
think
see.
You want to do the link by Watts, and you can pick up the phone, and I did that, and made a meeting with the rep, and like they're real. I know engineers have flown and looked at inspected them physically to make sure they were good for their buildings. I think Stet Sanborn, I showed his face earlier. He'd be one of those people that like flew to the factory to make sure it was real over in New York City or in upstate New York.
Excellent. I did a project in Solvang that is a little bit warmer and a little bit cooler than where I live in Santa Barbara, which is coastal. And we did all electric VRF. And the one thing, just for everyone's info, yeah, it was like that, only it was like, I think it had looked like a six-cylinder engine stuck on the roof. The parapets need to be taller when you retrofit these things. Like if you consider 5 feet is the height of a normal package unit, man, the VRF is probably closer to 7 feet tall when you get those little solar, whatever those things on the top are.
It's a place for the fan. There's a big fan in that little thing. They come in a lot of different form factors. Like AirMech system here is more of a block. It's not quite as tall. Here are examples. You know, these big systems. So this is kind of like the Mitsubishi looking one.
Yeah, that's the one we did. So we had it peaking up a little bit. And we had to do some stuff to tweak it on one project. But now that I know, I just know I got to get a little more parapet height for the VRF. But the VRFs are awesome. I think it replaced multiple package units and it cleaned it up. We had one unit on the roof where we probably have 6 normally. And I'd also have to figure out how to duct from the second floor, from the roof to the first floor through a second floor. And so we just run the refrigerant down there and everything can just be in the room and everyone's stoked because they can have stuff off when nobody's in there. It's not like just one thermostat. There's no temperature wars. Super cool.
Yeah. Thank you for that testimonial. Hey, Susan, I see your hand up. Thanks, Paul. And just, our guide is coming out. I'm going to try to, everything will be in there and we're almost there. Susan, do you want to ask your question?
Yes, I think it was an excellent presentation by both people and I really enjoyed it. And my question is related to an earlier presentation on the University of Irvine Medical Center, which is a net zero energy hospital. I was very excited about it because it used biomimicry and also progressive design build, and that's a whole nother thing. But they showed 4 mega electrical units. I mean, they were huge. And those were going to be the emergency backup. And they didn't have time to really go into it, but I I was just blown away because I've always felt like the hospital is one of the hardest building types to get all electric, but they did it. And I just wondered what was special. They looked unusual. They were square, white, big, and they were all in a row. And there were these big electric backup. Can you speak to that?
Well, I don't know if they're if you're saying they're backup power, they could have been generators and like natural gas generators in blocks up there, or they could be batteries. I didn't have a chance to get together this slide, but there's a bunch of community centers I can show you that are using batteries now. And there's one down in Palo Alto that just got approved to go with a big battery system instead of putting in what you often see as a diesel generator and sometimes a natural gas generator. Now, on this topic of hospitals, though, at least for all electric, aside from resiliency, which I'm going to say again, I think getting a big electric vehicle is actually the cheapest way to get resiliency and have like landscaping crew and such that keep the vehicles on site of a campus, make that vehicle available if there's a power outage, but otherwise just use it for the site. Hospitals, the main problem people have is they're used to using a boiler loop to heat incoming air because it's constant volume. You're always pushing clean air into all the rooms and exhausting it into a dirty air pipe, but you're not taking that air back into any rooms. So it's constant air volume that's always just like a windstorm essentially moving through a hospital. That sometimes is using a gas boiler. The right way to do it is put an electric resistance element into each of the rooms and just heat the air, or put in a cooling loop, but not also a heating loop. So you have a cooling loop and an electric resistance heater in these constant air volume little boxes to work with each room. And that's cheap and easy. And so I don't think hospitals are a big challenge. You know, that's all I say is I looked at all the different equipment and like, no, they're all over the world. People are doing all electric hospitals and clinics. Places like Kentucky, where there's a lot of mountains, makes it hard to put in infrastructure. Places like in Hawaii, where they're islands, hard to put in infrastructure. You just don't even see where Scott's brother lives in the panhandle of Florida. You don't see pipe work, but they definitely have hospitals and clinics, and they always have. So they're able to pull it off. Now, Ismar, I want to make sure. You said, hi, Mark. No, he's writing to Mark. Who's Mark? I saw your response on Basecamp. However, here in LA, we are having mixed feedback. Will Wright has provided a few editorials, and we are preparing for an upcoming 1.5 degree symposium. And under advocacy, we are mainly, Will and I, are looking further into the subject. I'm not really sure what the question is.
Hey, John, I think that's on another topic. That's on net metering. Hafsa has her hand raised for a question.
Oh, hey, yo.
Hi, Sean. Sean, I just had two questions actually. For one, I wonder what your thoughts are about a need for a study that can show how much energy these systems are actually using. Because the usage can only be justified if the source is clean, right? And then secondly, we're doing a retail shell in the city of Dublin, which hasn't adopted an all electric policy yet. And in planning infrastructure for like future restaurants, the MEP consultants were like, horrified about the energy needed to bring water up to 250,000 BTUs. And in most studies, for restaurants, cooking equipment is brought up, but the water heater, which is sized based on plumbing fixtures, is a little ignored. And if the restaurants have storage tank water heater, then the storage tank eats up a lot of kilowatts. And I wonder what your thoughts are, and if you have solutions that I could take back to the team.
Okay. Well, your first point, if you're using heat pumps, you're generally reducing the energy so dramatically because you're pulling energy from the environment. You probably have a COP, a coefficient of performance of 3, which means 1 unit of electricity and gets you gathered 3 units of heating or cooling from the environment. Whereas the gas burning stuff is usually somewhere between a COP of 0.6, maybe up to 0.9. That's pretty much where almost everything is. Maybe 0.95 for the very best, but it makes really no difference because even in West Virginia, which is 92% coal in its grid, studied this question. If you're using a high COP heat pump, high, just a 3, because they go up to like 9, just a 3. You are using less total energy because you're gathering most of it. You're producing less total pollution, even on an all-electric building in West Virginia, if you're using heat pumps, than if you were burning natural gas directly in the building. Sierra Club studied this in all 50 states, and they color-coded each state by how good it was. All states are good. Some states are excellent. But everywhere we go, it's a net energy reduction to use heat pumps because it's heat gathering. So that's cool. The second part, your question around the studying of them, the National Electrical Code gives two options when figuring out your power demand. One is a whole year study, especially during the coldest or the peak season. You have to make sure you focus on that. And if you do a whole year study of the utility bills peaks, that can be your baseline for then adding electrical load, as opposed to the other way of building it up from the code itself, like this much power for this device, this much power for this device. So these two different options, yeah, when you're going and retrofitting a commercial building, doing an annual study to the NEC code standards to determine what is your actual power allocation use, well, how much of your service are you using, so you can add more stuff on without having to be constrained by the other way of doing the code, like the methodology of analysis and spreadsheets and such. So I think you're sort of your third point of like how some of these devices can use a lot of electricity can be mitigated by going in and getting efficient stuff like the link by watts, that CO2 heat pump, that has a COP of about 4, not 3. That's great stuff. And there's ones out there that have COPs of 5. They're smaller. So you can get lower and lower amounts of power as you invest in more energy efficiency. But yeah, I mean, one other thing, if you have the therms, take your therms and you multiply it by 10, that's the amount of kilowatt hours. That's a whole, if you're using heat pumps. And one of the things that when you're going from gas, which is like cooking 25% efficient, to electric, which is 60 to 90%, that's essentially a 2/3 reduction, just like using a heat pump. So it turns out that really all the electric uses, the resistance ones and induction, and like dryers, for instance, all of those, they essentially use 1/3 as much energy as the gas device. Same thing with the heat pump. So in all ways, you're pretty much assuming like the end budget of energy is going to be 1/3 as much as it was when you're using gas. That's pretty cool.
Okay, I see there's another hand up, but we're at time. I have a 1:30 meeting, so I have to sign off. But Sean, Barry, I want to thank you both so much for your work and for sharing that with us today. It was fantastic. Barry Hooper, Sean Armstrong, champions. Thank you, guys.
Thank you so
With
much.
that, I will sign off. Thank you all.
Take care.
Thanks.